In linear algebra, the product A transpose A shows up everywhere, in projections, least squares, and normal equations. There's a short, elegant trick that proves this matrix is invertible wherever A has independent columns, and there's a special class of matrices where A transpose A doesn't just become invertible, it becomes the identity matrix. Let me show you both. Here's the theorem. If A is an m by m matrix with linearly independent columns, then A transpose A is invertible. Now, to prove that any square matrix is invertible, we need to show that its null space contains only the zero vector. The null space is the set of all x satisfying the matrix times x equals 0, so we assume A transpose A times x equals 0, and our goal is to prove that x must be the zero vector. Here's the trick. Start with the assumption A transpose A times x equals 0. Now multiply both sides on the left by x transpose. On the right side, x transpose times the zero vector is just 0. On the left side, we get x transpose times A transpose A times x. Now regroup the first two terms using associativity. X transpose times A transpose multiplied by AX equals 0. Here's the key observation. X transpose times A transpose is the same as AX transposed. That's a basic property of the transpose. The transpose of a product reverses the order, so the left side becomes AX transpose times AX, which equals 0. But what is this expression? AX transpose times AX is the dot product of AX with itself. In other words, the squared length of the vector AX, written as a formula, the norm of AX squared equals 0. The squared length of any vector is always non-negative, and it equals 0 only when the vector itself is the zero vector. So from the fact that the squared norm of AX equals 0, we can conclude that AX must equal the zero vector. Now we invoke our hypothesis. A has linearly independent columns, and this means the null space of A is trivial. The only solution to AX equals 0 is x equals 0. And with that, the proof is complete. Let's reflect on the key insight. Why did multiplying by x transpose work so well? It manufactured a dot product, converting a matrix equation into a geometric statement about the length of a vector. The squared length is always at least 0, so the only way it can vanish is if the vector itself is 0. This is the elegant bridge from algebra to geometry that makes the whole proof work. Independent columns guarantee A transpose A is invertible, but there's a special case where A transpose A becomes the identity matrix. This happens when A has orthonormal columns. Let's break the word apart. The left panel shows the orthogonal condition. Orthogonal means the columns are perpendicular. The dot product of any two distinct columns, Qy and Qj equals 0, whenever I is not equal to j. The right panel shows the normal condition. Normal means each column has unit length. The norm of Qy equals 1. Both conditions are required. Here's an important counterexample. The vectors 3, 0, and 0, 5 are orthogonal. They are perpendicular because their dot product is 3 times 0 plus 0 times 5, which equals 0. But they are not orthonormal because their lengths aren't 1. The vector 3, 0 has length 3, and the vector 0, 5 has length 5. You need perpendicularity and the unit lengths together. When both conditions hold, we call the columns orthonormal, and the beautiful result is that A transpose A equals the identity matrix. Let's start with the simplest case. Let A be the 3 by 3 identity matrix. We can write A with columns. E1 equals 1, 0, 0, E2 equals 0, 1, 0, and E3 equals 0, 0, 1. Each column has norm 1. Each pair of distinct columns has dot product 0, so the columns are also normal. Now let's compute A transpose times A. Remember the entry in row I, column j of A transpose A equals the dot product of column I with column j. Let's fill this in entry by entry. E1 dot E1 equals 1 times 1 plus 0 times 0 plus 0 times 0, which equals 1. E1 dot E2 equals 1 times 0 plus 0 times 1 plus 0 times 0, which equals 0. Similarly, E2 dot E3 equals 0 times 0 plus 1 times 0 plus 0 times 1, which equals 0. Following this pattern, every diagonal entry is 1 because each column dotted with itself gives 1, and every off-diagonal entry is 0 because distinct columns are orthogonal. Therefore, A transpose A equals the 3 by 3 identity matrix. This confirms our property for the simplest possible example. Now let's look at a non-trivial example. In R2, define Q1 as the vector cosine theta, sine theta, and Q2 as the vector negative sine theta, cosine theta. First, let's check that these vectors have unit lengths. The norm of Q1 squared equals cosine squared theta plus sine squared theta, which equals 1 by the Pythagorean identity. The same calculation gives the norm of Q2 squared equals sine squared theta plus cosine squared theta, which also equals 1. Next, check perpendicularity. Q1 dot Q2 equals cosine theta times negative sine theta plus sin theta times cosine theta. That simplifies to negative cosine theta, sin theta plus cosine theta, sin theta, which equals 0. Both conditions hold for every value of theta, so these two vectors are also normal regardless of the angle. Now form the matrix A with columns Q1 and Q2. Since the columns are orthonormal, A transpose A equals the 2 by 2 identity matrix. Geometrically, these vectors form a rotated coordinate frame on the unit circle. As theta changes, both vectors rotate together while always remaining perpendicular and of unit length. Here's why this matters. The general projection formula reads P equals A times the quantity A transpose A inverse times A transpose. Now, when A has orthonormal columns, we showed that A transpose A equals the identity matrix I, and the inverse of I is just I itself. So let's substitute this into the formula. The quantity A transpose A inverse gets replaced by I. This gives us P equals A times I times A transpose. But multiplying any matrix by the identity matrix leaves it unchanged, so the I gets absorbed. We are left with the beautifully simple result, P equals A times A transpose. The matrix inverse vanishes entirely. No inversion computation is needed. This is a massive simplification for both theory and computation. Two key results to carry forward. First, the null space trick. Assume A transpose A times X equals 0. Multiply both sides on the left by x transpose to get x transpose A transpose AX equals 0. But this expression equals the squared norm of AX, that is, the length of AX squared equals 0. If the columns of A are linearly independent, then AX equals the 0 vector forces X itself to equal 0. This template, proving invertibility by showing the null space contains only the 0 vector, reappears throughout linear algebra and optimization. Second, also normal columns collapse R transpose A to the identity matrix, removing inversion from every formula that depends on it. This underpins QR factorization, the Gram-Schmidt process, spectral decomposition, and the simplified projection formula P equals AA transpose. So here is the full spectrum. Independent columns guarantee that A transpose A is invertible. Also, normal columns guarantee that A transpose A equals the identity. That's the spectrum from it works to it's effortless.